One of the outstanding design features which affects flight in the AH-1 is its slim silhouette. The slim silhouette and other streamlined characteristics result in an increased speed envelope, which demands increased attention by the pilot to keep his planning and judgment far ahead of the aircraft during all maneuvers. Another design feature which stems from the slim silhouette and which distinguishes the AH-1 is its tandem seating. To carry out the Cobra's mission as an attack helicopter, the gunner is positioned in the front seat and the pilot in the rear seat. The gunner's floor-mounted, flexible sight prohibits use of standard configuration cyclic and collective controls in the front station. Therefore, sidearm controls have been installed to provide the gunner with piloting capability. However, because of their short length, they operate through only 1/4 the normal stick travel. This results in extreme sensitivity. The initial reaction of the student when piloting up front is to over-control the aircraft. On the other hand, the gunner is provided with unprecedented visibility for both target engagement and piloting the aircraft. In contrast to the front seat, the pilot is provided with conventional flight controls which are more familiar to the aviator who has had UH-1 experience. However, his visibility from the rear seat is somewhat restricted due to the configuration of the instrument panel and the pilot's fixed sight, as well as the presence of the gunner in the front seat, especially during approaches. In marked contrast, when in an attack attitude, the Cobra pilot's visibility in the rear seat is outstanding. The pilot also has excellent side vision from the rear seat, for example, in low-level tactical reconnaissance. Now that you have been introduced to the Cobra's basic flight characteristics, including the essential differences between the front and rear stations, let's see how the basic flight maneuvers are performed. Since most of you already know how to perform these maneuvers in a conventional helicopter, we will cover only those aspects which are affected by the Cobra's unique characteristics. Perhaps the best way to accomplish this will be to follow an instructor pilot and one of his students during pertinent segments of transitional training in the AH-1. One of the first maneuvers the student will encounter is hovering the aircraft from the front seat. The IP directs the student to increase the collective pitch control with a smooth, constant, positive pressure and apply anti-torque pedals to maintain heading. As the helicopter breaks ground, minor corrections with the cyclic are required for a stabilized vertical ascent until a hovering altitude of 3 feet is reached. As you have seen, the initial tendency of most students is to over-control in the front seat. However, as training progresses and the student becomes more comfortable, he will be able to correct this tendency. Later in his transitional training, when the student hovers the aircraft from the rear seat, he will find the conventional controls more comfortable and easier to handle. As we have already seen, visibility from the rear seat is often a problem, and this applies to the hover. In the Cobra, the aviator is sitting higher above the ground at a 3-foot hover than he is accustomed to. This requires the student pilot to make a conscious effort to use all the visible areas available to him. When landing the Cobra from a hover in the rear seat, the aviator cannot see the ground beneath. Therefore, it is essential that he maintain a smooth, constant rate of descent and make necessary cyclic corrections to effect a smooth touchdown. The next basic maneuver the student will perform is a normal takeoff from a hover in the rear seat. He must make a 90-degree clearing turn to the downwind leg prior to initiating this maneuver at the stage field. He must also make a pre-takeoff check and call out instrument readings to the IP. These consist of RPM, caution or warning lights, all instruments in the green, fuel quantity, the highest oil temperature, rain removal, and ECU off. A typical pre-takeoff check might sound like this over the Cobra's intercom.
6,600 RPM. No caution or warning lights. All instruments in the green. 1,400 pounds of fuel. Highest oil temperature is 65 degrees on the engine. Rain removal and ECU are off.
There are two types of normal takeoffs available to the aviator, from a hover or from the ground. In the Cobra, the choice is dependent on gross weights, power available, and outside conditions. Hover power should be checked to make this determination. Since the Cobra is operated in combat at maximum gross weight conditions, the aviator must constantly keep in mind the aircraft's capabilities and plan accordingly. When making a normal takeoff from a hover, gentle forward cyclic pressure must be applied to avoid an excessive nose-low attitude, which in turn would result in pulling excessive power. Because his forward vision is partially blocked in the Cobra's rear seat, the student must again look around the pilot's fixed sight to maintain the desired ground track. Heading and altitude are maintained until effective translational lift has been obtained. The student then adjusts cyclic and collective to obtain a normal climb of 80 knots indicated and 500 feet per minute. Now the student is making his clearing turn and pre-takeoff check for the next maneuver, a normal takeoff from the ground. This training maneuver is not necessarily the same as on an actual takeoff under maximum gross load conditions, which would be employed when flying the AH-1 in combat. However, it does closely parallel this maneuver and will be used during your training to develop the control touch and coordination required to execute the combat maneuver. No more than hover power is used to perform this maneuver. To initiate a normal takeoff from the ground, the student pilot applies collective to get the aircraft light on the skids, maintaining neutralized cyclic and pedal settings. He then places the cyclic control slightly forward of neutral and simultaneously increases collective pitch. The aircraft should break ground and accelerate forward simultaneously. Minimum altitude is desirable until effective translational lift is obtained. A slight power adjustment may be required, although it should not exceed hover power at this point. The student initiates a shallow climb angle with the cyclic that will allow the aircraft to clear any barrier safely. Once again, the student must recognize the Cobra's rear seat visibility restrictions in maintaining a ground track. Once the barriers are cleared, power is adjusted to establish a normal climb. Traffic patterns utilized at the stage field are of the conventional type. However, the Cobra is operated at higher airspeeds in these patterns than those to which the student has previously been accustomed. This places a special premium on the requirement for the aviator to constantly plan ahead of the aircraft. In most other respects, traffic patterns are performed in essentially the same manner as in other helicopters with which the student is already familiar. Now let's return to the beginning of a stage field traffic pattern. The first instance in which the Cobra's greater airspeed manifests itself during a traffic pattern is after takeoff on the takeoff leg. An airspeed of 80 knots and a climb of 500 feet per minute are maintained until the established pattern altitudes are reached for the takeoff and crosswind legs. The downwind leg is flown at 100 knots, which makes it important for the aviator to remain especially alert during a pre-landing check as he divides his attention between maintaining the ground track, observing the flight instruments, and announcing the check to the instructor. The pre-landing check is the same as the pre-takeoff check. The base and final legs are flown at the appropriate altitudes and airspeeds for the intended approach. When turning from base to final, the Cobra's higher airspeed and the visibility restrictions in the rear seat make it especially vital that the student pilot utilize advanced planning and judgment to assure proper lane alignment. Now let's see how the Cobra's unique capabilities and flight characteristics affect the normal approach. We've seen several examples of how the pilot's fixed sight restricts forward vision when flying the aircraft from the rear station. When making an approach, this restriction becomes even more evident. At the stage field, lane alignment at the desired airspeed and altitude is the first requirement. Upon intercepting an 8 to 10 degree angle to the intended landing point, power is reduced and then adjusted to maintain this angle. The pilot will again have to look around the fixed sight to maintain the angle. Closure rate is controlled by appropriate cyclic movements and shifting vision out to the 90-degree position to check apparent ground speed. To determine the correct closure rate, the apparent ground speed should be that of a man walking briskly. Due to the aerodynamically clean configuration of the Cobra, the pilot must divide his attention between maintaining this desired closure rate and maintaining the proper angle more than he has been accustomed to in other aircraft. The type of termination, either to a stationary hover or to the ground, will not affect the approach until approximately the final one-third. When terminating the approach to a hover, the touchdown point will drift down the windshield and out of sight. Attention must be shifted to those areas adjacent to the panel for angle determination and altitude reference. Keep in mind that the aviator in the rear seat is positioned higher above the ground in the tandem seating configuration, and power should be adjusted appropriately to terminate at a stationary 3-foot hover above the panel. When making a normal approach to the ground, the first 2/3 of the approach are basically the same as before. However, on the final 1/3, airspeed and altitude are simultaneously dissipated to effect a smooth touchdown on the panel. Again, referencing areas adjacent to the intended landing point are required. He continues flying the angle to the ground, touching down with a minimum ground roll. These two maneuvers are essential in developing the planning, judgment, and control touch required to land the Cobra under maximum gross weight conditions in possible unprepared areas. The termination with power auto-rotation is designed to develop the skills, reaction, and judgment required of the pilot to make safe auto-rotative descents in the Cobra. Now, let's go back to the start of this maneuver and observe the key procedures which apply to the Cobra. Again, the student is in the rear. With the aircraft at 100 knots, the first step is to align the Cobra with the intended area, in this case, a lane at the stage field. The section of the entry point should be such that an auto-rotated descent at a 70-knot altitude will allow the aircraft to terminate with full power at a 3-foot hover in the center portion of the lane. A rule of thumb for the entry point is an angle slightly greater than a steep approach to the center of the lane. Because of the Cobra's clean configuration, a smooth, simultaneous entry is essential. Collective down, throttle to flight idle, trim cyclic aft to a 70-knot altitude, and announcement of rotor and gas producer RPM. Because of the fixed sight, it becomes especially difficult to see the lane from the pilot station once established in the 70-knot altitude. Attention must be divided among instruments, horizon, and side views in order to determine the effects of the pilot's control input. If the descent does not follow the intended plan and the termination would be outside the prescribed lane space, a power recovery should be executed. Smoothly increase the throttle to full open until the needles are rejoined. And execute a go-around prior to passing through 100 feet above the ground. Due to the rapid acceleration rate of the L-13 engine in the AH-1, the throttle must be rolled on slowly to prevent an overspeed condition. If the descent is proceeding as planned and no more power recovery is required, rejoin the needles prior to passing through 100 feet above the ground. Assume a decelerating attitude between 50 to 100 feet to reduce airspeed and rate of descent. This should be very close to an actual landing attitude. At 10 to 15 feet, make an initial pitch pull, and then pushing with power to terminate at a 3-foot hover at or near zero airspeed. One basic maneuver in which the pilot must become extremely proficient is the forced landing. At this time, we will discuss simulated engine failure only in the speed envelope of 120 knots and below. Simulated failures at higher airspeeds will be discussed during advanced maneuvers. When flying the AH-1, particularly at relatively low altitude, the pilot must be continually alert for suitable forced landing areas. Although the fixed sight and instrument panel restrict forward vision, we have seen that visibility to the sides is excellent. A practice forced landing is initiated by the instructor with the throttle reduction and the announcement, forced landing. Immediately, the student pilot enters auto rotation and turns toward the intended landing area if necessary. Wind direction should be considered, but not be the decisive factor in selecting the area. Rapid vision transition and prior planning will aid in area selection. When establishing a 70-knot auto-rotated descent, he cross-checks and announces the rotor and gas producer RPM. He also makes a practice mayday call on the intercom. The airspeed can be adjusted if required to maneuver toward the desired landing area. The clean configuration of the Cobra dictates a minimum rate of descent of 65 to 75 knots. Best speed for descent and flare is 70 knots, and best distance speed is 85 to 95 knots. All simulated forced landings should be terminated with a power recovery at least 200 feet above the highest obstacle. The purpose of the maneuver is to develop skills in reacting to an emergency situation should it occur. These, then, are some ways in which the AH-1 Huey Cobra's flight characteristics affect basic maneuvers. As you have seen, constraint and awareness of the differences which characterize the Cobra, as well as alertly planning ahead, are absolutely essential during transitional training in an aircraft whose speed and maneuverability far exceed the experience of most helicopter pilots. Recognition of these requirements is an important step toward making your transition to the AH-1. UH-1 Huey Cobra presents a new flight realm to most helicopter pilots who are accustomed to slower, lighter, or less maneuverable helicopters such as the UH-1 Huey Cobra. Advanced maneuvers, particularly those performed at high speeds or maximum gross weight, demand a far greater element of maneuver planning. In order to operate the Cobra within safe limits, with the greater rates of descent and higher G-forces it is capable of developing, mastery of advanced maneuvers is essential. Here are the advanced maneuvers with which this film is concerned. A shallow approach and running landing is used to land at speeds above translational lift, under high-density altitude or gross weight conditions, and certain types of emergencies. A running takeoff allows a heavily laden Cobra to develop translational lift through forward speed before takeoff. A steep approach is used to land in confined areas. In the Cobra, the pilot's instrument panel reduces visibility downward and forward. A maximum performance takeoff is used to fly a Cobra out of confined areas over obstacles safely. A 180-degree auto rotation is a precision maneuver that improves pilot skill and ability to land safely without power. Hovering auto rotation requires fast reaction to cushion touchdown after loss of engine power at low altitudes. High-speed maneuvers over 120 knots indicated airspeed bring into play the outstanding differences in the Cobra's flight envelope. Steep banks, high-speed turns, high-speed dives with full stores. Maneuvers like these often place the aircraft close to its design limits and must be judged carefully, even in the heat of combat. Now, here are the requirements and procedures of the individual advanced maneuvers. The major requirements for a shallow approach are proper alignment at the approach altitude, an entry airspeed of 80 knots, with a constant approach angle of 5 to 8 degrees. As the entry point is reached and the aircraft begins to decelerate below 80 knots, plan to use cyclic as the major control, both to slow the airspeed and to control the angle of approach with selective at minimum realistic pitch setting. Once deceleration is complete, add collective pitch as necessary to maintain approach angle, keeping airspeed above translational lift, using only the power required and no more. Now here is the procedure for the shallow approach and running landing in detail. As the entry point is approached, line up with the landing lane or touchdown point. With the reduced forward visibility available in the rear cockpit, it is important that you pick out visible reference landmarks near the touchdown point, as you will not be able to see it when you land. Once the aircraft has been slowed to the entry speed of 80 knots, reduce collective to achieve the approach angle of 5 to 8 degrees. For training purposes, limit power to 1% less than that required to hover. Then rely on cyclic for major control of deceleration and approach angle. Maintain constant approach angle and proper rate of closure, as evidenced by steady apparent enlargement of the landing area. Continue to decelerate on the constant approach angle. Plan to use as little lateral cyclic as possible. Keep any turn shallow. Below 50 feet, maintain ground track by slipping the aircraft if necessary. Once deceleration is complete, maintain airspeed above translational lift with cyclic control and collective. Cushion the landing as much as possible. If the landing attitude is tail low, remember the Cobra's tail skid is much lower than the Huey. Now let's run through it again. Maintain approach angle mainly with cyclic control down to 35 knots. Use collective below this to maintain angle, but only what is necessary. Do not lose translational lift. When the Cobra is heavily laden, or during high-density altitude operations, it might not be able to perform a normal takeoff from a hover or ground position. For training purposes, it is beneficial to practice the running takeoff, simulating maximum gross weight. Major requirements for training purposes are make a stabilized 2-foot hover to determine maximum allowable power and head into the wind, with prior planning of the takeoff route as the takeoff angle may be shallow. Set down again. On takeoff, smoothly accelerate to ETL. Care must be exercised during nose-low takeoffs to avoid ground contact with the nose turret. Here is the procedure for the running takeoff as practiced in training in detail. First, to determine maximum allowable power for practice purposes, hover in the direction of takeoff. Stabilize at a 2-foot altitude. Note the percent of N1 RPM required. Return the aircraft to the ground to calculate maximum allowable power. Perform pre-takeoff checks. Plan the takeoff route and make sure there is enough room ahead for a short ground run. With cyclic neutral, apply enough power to cause the aircraft to become light on the skids. Attitude should be the same as in normal takeoff. Add collective gradually up to maximum allowable power. Plan to limit allowable power to 1% less than the power required to hover. If the Cobra is still stuck, try walking the pedals until forward motion is achieved. Continue to control attitude with cyclic to prevent premature liftoff. Hold the same takeoff attitude. Avoid nose-low attitudes that might pitch the forward chin turret into the ground. Concentrate on a smooth acceleration. The aircraft will leave the ground when sufficient speed has been attained for effective translational lift. At this point, 0.5% N1 loss is customary and must be reapplied by adjusting collective. Maintain allowable power setting and adjust climb angle to ensure clearing the barriers. When climb speed has been reached, rotate the nose to normal climb attitude. As the climb after a running takeoff is usually shallow, shallow turns are acceptable to avoid obstacles. The steep approach and landing maneuver is used to get into confined areas. to avoid turbulence, rough terrain, or congested areas. Major requirements are a slow, steep angle of descent, no more than necessary, maximum 12 to 15 degrees. A good track at an entry altitude of about 400 feet with an entry airspeed of about 80 knots. Visual analysis of apparent ground speed to obtain correct rate of closure. Expect loss of translational lift. Add power to compensate for this loss and maintain heading. Now here is the procedure for the steep approach and landing in detail. Establish a good track on the final approach lane, using a crab to intercept the proper approach heading as necessary. Initiate the steep approach by reducing collective, intercepting a steeper angle of approach than normal, usually about 12 to 15 degrees maximum. For any given situation, the approach angle should be only steep enough to have a clear downward approach to the touchdown point. You should obtain references near the touchdown point. Continue to use collective pitch control slowly to correct deviations from the desired line of descent. Hold slow cruise attitude, about 80 knots, with corrections to airspeed accomplished by momentary attitude changes. Maintain the entry airspeed of 80 knots as the Cobra descends until the apparent ground speed and rate of closure seem to be accelerating. Then decrease the airspeed and adjust the rate of descent until the apparent ground speed is about as fast as a man can walk at a brisk pace. At about 100 feet AGL, as forward speed is gradually reduced to about 40 knots, loss of translational lift may be expected. To compensate for this loss and maintain approach angle, add collective pitch. At about 50 feet, align the aircraft with the approach heading. Terminate the landing as in a normal approach. The maximum performance takeoff is used to leave confined areas. It is a smooth, slowly developed maximum angle takeoff with a highly efficient steep angle climb established by using maximum allowable power. Takeoff attitude is maintained until all barriers are cleared. Be sure you have enough power to complete the maneuver successfully before attempting takeoff. Here is the procedure in detail. First, determine the amount of power required to make a stabilized hover. Lift off. Stabilize at a hover 2 feet AGL in the direction of takeoff. When stabilized, note the engine N1 RPM required to hover. Land from the hover to make go, no-go calculations and cockpit checks on the ground. Check the low point of real or simulated barriers. Note the outside air temperature. If the percent of engine N1 RPM required to hover does not exceed that listed on the go, no-go placard for the OAT reading, the Cobra has sufficient power for takeoff. For training purposes, if more than enough power is available, limit the allowable power to no more than 2% over that required to hover. After all interior cockpit checks are completed, clear the aircraft as the last procedure before takeoff. The Cobra's tandem seating arrangement gives increased visibility, especially to the sides, so one man, the pilot, can make this check. Note again the low point in the barrier that must be cleared. The attitude of the Cobra on the skids at rest is about the same as a 40-knot attitude. This is the most efficient attitude for maximum performance takeoff. Plan to establish and maintain this attitude up to 100 feet above ground level. Ensure a neutral cyclic control position so that inadvertent attitude changes on liftoff are minimized. Adjust cyclic laterally on the ground for crosswind takeoffs to control drift. Gradually and continually add collective power and left pedal until the aircraft is light on its skids. Make minor cyclic and pedal adjustments as necessary. Shift attention to the horizon or barrier, continuing to add power smoothly to effect liftoff. Control attitude and drift with cyclic and pedal to maintain heading. Check the gas producer N1 RPM to avoid over-application of collective. Stabilize collective at maximum selected allowable power. As ETL is entered, adjust cyclic to retain the 40-knot attitude. Establish crab passing 50 feet to hold desired ground track. By now, airspeed indicator should show an increase, but will not normally reach 40 knots until more than 100 feet. If the pre-takeoff calculations were correct, the barrier will be cleared. If not, try more practice at limited allowable power. As the barrier is cleared, apply sufficient forward cyclic to accelerate to normal airspeed. A successful maximum performance takeoff is a pleasure to watch, and for the successful Cobra pilot, an even greater experience, especially when the alternatives are considered. Remember that variations in operational conditions, such as density altitude, can have an important effect on engine performance. So allow a good margin of safety for this important maneuver. A 180-degree auto-rotation is one of several precision auto-rotative maneuvers open to the pilot to help him reach a pre-selected touchdown point. In this case, either right or left of a Cobra heading downwind. Requirements are a point of entry at about 800 to 1,000 feet AGL, entry airspeed 100 knots, descent at 70 knots, rotor RPM 294 to 324, once aligned with the lane. The requirements are the same as for precision auto-rotation. Once again, caution should be exercised in tail-low landings because of the low tail skid on the Cobra. As in a straight-in precision auto-rotation, you can make use of 5 variables: entry point, airspeed, rotor RPM, deceleration attitude, and pitch application to assist you in reaching the predetermined touchdown point. In addition, you make a 180-degree turn in this maneuver. The entry point selected will influence the other variables. An entry point at a range greater than that for a basic auto-rotation will mean controlling airspeed and rotor RPM to extend the glide. It is easier to extend than to shorten the glide. Plan accordingly. Usually, the need for auto-rotation arises when the engine or some other subsystem fails. Then the pilot has no choice as to his initial conditions. The first step in the procedure is reduce collective pitch. Flight idle and trim the aircraft. Maintain rotor RPM in the green. Avoid the common mistake of rushing lateral cyclic to start the turn before trimming or simultaneously with collective reduction. This would result in high sink rates. The tandem seating arrangement of the Cobra allows the pilot good visibility on either side. Plan to start when the touchdown point comes abeam at about 200 to 300 meters. Apply aft cyclic for a smooth deceleration to a 70-knot attitude. For the turn, adjust angle of bank to ensure rollout aligned with the touchdown area. Make frequent visual checks of rotor RPM during descent, keeping within allowable limits. Remember that RPM builds much faster in the Cobra than in the Huey during auto-rotative turns, especially in a right turn. Adjust collective pitch if necessary to keep the rotor RPM within limits. Plan the rollout from the turn to be in line with the touchdown point, slipping as necessary in crosswind. Attitude changes are usually slight and easiest to control with a steady aft cyclic pressure during the turn in normal wind conditions. As rollout is completed, maintain 70-knot attitude. At about 50 feet, decelerate to decrease forward airspeed and rate of descent. Return collective to full down position to avoid rotor RPM decay in the straight portion of the descent. Maintain attitude horizon reference to avoid too fast an airspeed and rate of descent. At about 15 feet, apply initial pitch. And at 3 to 5 feet, apply sufficient collective pitch to cushion the landing. Remember that the tail skid is lower than the Hueys by a significant amount. A hovering auto rotation is practiced to develop fast pilot reaction. It requires a vertical descent and a soft touchdown with no lateral drift. Here is the procedure for the hovering auto rotation in detail. Pick up the aircraft, head into the wind, and stabilize at a 3-foot hover. As soon as the aircraft has been steadied, close throttle to flight idle position, being careful not to change pitch. Simultaneously apply right pedal as required to maintain heading. Apply cyclic control to maintain level attitude. About a foot off the ground, apply collective to cushion the landing. After ground contact, with the helicopter resting on the ground, smoothly lower collective to full down position. Apply sufficient cyclic to level the rotor system. A final caution: do not attempt to execute a power recovery once a hovering auto rotation is initiated. Up to 120 knots indicated airspeed, the AH-1 Cobra is similar to the UH-1C Huey. Above 120 knots, the Cobra's flight characteristics are markedly different from slower helicopters and must be considered in all high-speed maneuvers. For example, higher speeds greatly increase the importance of pitch-cone coupling, a design feature of the 540 rotor hub that helps fight blade stall and makes it easier to fly the aircraft. The principle can be demonstrated on this wooden model. Simple door hinges on the model illustrate how the flexure plate at the center of the rotor hub is designed to do most of the bending or coning of the rotor blades under G-loads from severe maneuvers. This differs from most rotor systems in which the blades bend along their length. By mechanical linkage with the pitch change tubes, the pitch horns automatically reduce blade pitch as the blades cone under loading and convert the loading into higher rotor RPM. Severe overloading under the stress of high speeds of high G-loads can cause an overspeed condition unless the pilot uses collective to keep RPM within limits. The Cobra's high degree of maneuverability makes it imperative that you understand the effect of pitch-cone coupling and use correct collective coordination to keep RPM within limits. The design of the 540 rotor system is a factor in the increased effect producing the phenomenon of transient torque during turns. Transient torque is the increase of decrease of torque resulting from the momentary change in drag of the advancing blade during the turn. Transient torque can put the aircraft up against its design limits unless the pilot anticipates and corrects for it. Remember that transient torque is affected by the rate of roll rather than the angle of bank, which determines G-forces. In a left roll, momentary over-torque may result because the advancing blade increases pitch. You must remove torque before this happens. Remember to add torque again when coming out of the left roll. In a right roll, the advancing blade decreases pitch, and the rotor system tends to increase RPM. Here, the torque will drop accordingly, and overspeeding may result unless you again anticipate by adding pitch. Or, if you add collective for maneuvering, care should be exercised to avoid over-torque in the rollout. Avoid abrupt cyclic movements during high-speed flight. In allowing for transient torque, consider a rollout left or right, the same as a turn in that direction. You must also allow room in high-speed turns. Turning radius varies as the square of the speed. The Cobra on the left is traveling at 80 knots. The Cobra on the right at 160 knots. This means the Cobra on the right required 4 times the turning radius as the one on the left traveling 80 knots at the same angle of bank. High-speed dives offer no particular difficulty during descent, but you must allow considerably more altitude for pullout, since rates of descent of 2,000 to 3,000 feet per minute are common in the Cobra. You must know how much power you have available to overcome the G-forces of the pullout. If you don't have enough, the aircraft will mush on down, giving up altitude or airspeed or both before pulling up. This is probably the most important flight characteristic to be learned and anticipated by pilots accustomed to the Huey as they make the transition to the Cobra. The AH-1 Huey Cobra's improved capabilities mean a more effective airborne weapon system. Pilot mastery of advanced maneuvers can play an important part in the contribution of the Cobra and of Army aviation to the support of ground forces.
The aerodynamic flight characteristics of the AH-1 Huey Cobra are similar to those of other helicopters, such as the UH-1 Huey series, up to 120 knots indicated airspeed. Over 120 knots, the higher airspeed, lower drag, and higher maneuverability of which the Cobra is capable bring out latent characteristics and present a flight envelope that is new to you helicopter pilots who are accustomed to the UH-1 series. Those of you who have flying experience in fixed-wing aircraft or turbine helicopters will find transition to the AH-1 easier. When carrying out the more aggressive tactics for which the aircraft is designed, earlier thinking and maneuver planning are necessary. Thorough understanding and utilization of its different flight characteristics are mandatory. Here are the major flight characteristics covered in this film. Retreating blade stall, characterized by airframe vibration, nose up and left roll. If not recognized and corrected at once, it can deteriorate rapidly. Pitch cone coupling, a design characteristic that helps fight blade stall. In fast rolls and turns, transient torque appears due to changes in efficiency of the rotor system. In severe turns or pullouts, G-loading is important. Since the Cobra can go into steep banks up to and beyond the vertical, it is important to understand how the angle of bank and the available thrust of the rotor system set up and counteract G-forces. High speeds generally increase the distance needed to perform pullouts and turns. Turning radius, for example, varies as the square of the airspeed. Most of the aerodynamic forces that magnify the Cobra's flight characteristics come into play during recoveries from high-speed dives. Because the Cobra will often be required to operate close to its design limits, Severe maneuvers are particularly susceptible to other operating variables, such as rate of descent, density altitude, drag, gross weight, and RPM. Now, here are the major aerodynamic flight characteristics of the AH-1 Huey Cobra in greater detail. Two-bladed rotor systems have an inherent tendency for the retreating blade to develop a stall area during forward flight. Retreating blade stall is a danger well known to helicopter pilots like you. Increasing the angle of attack increases the lift of an aircraft up to a certain point. Beyond this point, increasing the angle of attack further causes the airflow to separate from the aircraft, in turn causing burbling and blade stall. Increased velocity of the airfoil due to excessive forward airspeed causes the same effect. A common example of increased angle of attack is in adding collective pitch to hover or achieve vertical climb. Lift from increased velocity of airflow is gained when the Cobra passes through the point of effective translational lift, then gains altitude. Retreating blade stall imposes an upper limit on forward airspeed. Here's why. In the hovering mode, lift is distributed equally over the rotor disc. There is an area of zero lift extending in a concentric circle around the rotor hub. At slower forward speeds, the area of zero lift or stall area of the blades is minimized. The relative wind of any forward speed, however, causes dissymmetry of lift between the advancing and retreating blades. The pattern of incipient stall or zero lift shifts to the retreating blade side. As the Cobra goes even faster and relative wind increases, the tip speeds of the blades are added to the forward airspeed on the advancing side and subtracted on the retreating side, resulting in a loss of lift. Eventually, any helicopter that goes fast enough will reach a critical airspeed at which the lift of the retreating blade can no longer be made equal to that of the advancing blade, causing retreating blade stall. High G maneuvers will also contribute to this effect. The blade tip stall at first shows up as vibration and buffeting of the airframe. The nose of the aircraft pitches up, and the aircraft tends to roll left as the rotor disc loses lift in the left rear quadrant. This becomes more severe as the area of lost lift spreads. Unless the basic cause, high angle of attack on the retreating blade, is corrected, control of the aircraft may be lost. Even if the aircraft recovers or seems to recover from the initial nose-up left roll symptom, without corrective action, the basic aerodynamic situation is unchanged and dangerous. After the initial vibration in the airframe, you will feel cyclic feedback. Reduce collective first, then apply aft cyclic to reduce airspeed and reduce the severity of the maneuver. Then increase rotor RPM. Note that the aft cyclic correction tends to keep the nose up. This is not a natural pilot reaction unless you recognize the problem. Remember, blade stall is rare in the Cobra in level flight, but it is made more likely with high gross weight, altitude, low RPM, and high G maneuvers. The operating limits decal will also serve as a constant reminder of the airspeed limitations during operations, and will assist you in pre-planning maneuvers to avoid blade stall. In addition, a design feature of the 540 rotor system pitch cone coupling helps you fight blade stall by reducing pitch under loading. Pitch cone coupling is known to pilots of the UH-1C model helicopter. However, like the other flight characteristics of the Cobra, it is much more important at increased speeds and G loads. The principle of pitch cone coupling can be demonstrated on this wooden model representing the rotor hub assembly. Under the stresses of high speed and high G maneuvers, the blades of most two-bladed semi-rigid rotor systems bend, or cone. In most helicopters, such as the Huey, the blades cone more or less along their entire length. This is not true of the Cobra's 540 rotor system. The flexure plate at the center of the rotor hub assembly is designed to do most of the bending, while the blades remain relatively rigid as the rotor system cones. The bending of the flexure plate is simulated on this model with ordinary hinges. Note that the links representing the pitch change tubes are disconnected. In this case, as the blades cone up, the ends of the pitch horns are free to move down, and the blade pitch remains unchanged. But the pitch change horns are mechanically linked to the pitch change tubes in practice. This means that when the blades bend or cone up, the pitch change horns cannot move down. But they automatically push up the trailing edges and reduce the pitch of the rotor blades instead. This can occur either during power flight or auto rotation, anytime a load is imposed on the rotor system. Pitch cone coupling is an automatic mechanical design feature that is said to unload the rotor system. It must be thoroughly understood and anticipated by the pilot. While it helps fight blade stall at high speeds, it is also possible that excessive rotor RPM will result, unless you closely monitor the instrument panel. If loading is increased severely, the rotor RPM may overspeed above the red line. If this happens, increase collective to replace the washed-out pitch. Fast rolls and turns bring out another flight characteristic of the Cobra. Transient torque is an effect of the momentary increase or decrease in the efficiency of the rotor system during turns. In a right turn, the effect is a sudden decrease in torque as the rotor system is unloaded. The pilot may have to add torque to prevent overspeeding. You may prefer to use more collective, either to tighten the turn or to keep from losing altitude. This will add torque to counteract the loss from the right roll. Transient torque can be dangerous, especially in left turns. A left rollout is the same as a left turn as far as the effect of transient torque is concerned. Now the rotor system receives an additional load. It can easily cause an over-torque condition which you must anticipate. Torque reduction may be necessary before starting the roll to avoid over-torquing the aircraft. Avoid abrupt cyclic movements. Reduce collective power if necessary. Another important aerodynamic flight characteristic, especially during steep turns and pullouts, is G-loading, the gravitational or centrifugal force acting opposite to the hub axis of the rotor system. The Cobra is capable of extreme maneuvers that make it relatively easy to impose G-loads that cannot be overcome by the thrust available. Before starting any maneuver involving G-loads, you must have a precise idea of whether or not you will have enough G capacity to sustain the maneuver. Let us review G-loads in principle as they apply to the Cobra. In any helicopter, the simplest example of G-loading is in vertical ascent or hovering. The tip-path plane of the rotor blades is horizontal. Thrust and lift provided by the rotor system combine to act upward vertically, opposite to the weight of the aircraft and any drag of vertical descent. When hovering, the sole downward force is essentially the force of gravity, or the weight of the aircraft. To sustain the hover, the rotor system must overcome the acceleration of gravity, or 1G. Assuming a gross weight of 9,500 pounds, at least an equal amount of rotor thrust, or G capability, must be produced to hover. The Cobra has approximately 21,000 pounds of thrust maximum available on a standard day. This figure varies from one aircraft to another and must be verified in terms of the day's operating conditions. Using the formula for computing G capability, The 9,500-pound aircraft has 2.21 times as much thrust as it needs to overcome the G-load of a hover. The remaining amount of thrust, 11,500 pounds, is available for maneuvering. In any kind of helicopter flight, including horizontal or vertical components, the lifting thrust of the rotor system acts perpendicular to the tip path plane along the hub axis. This resultant power tilts with the rotor, overcoming weight and drag with horizontal and vertical components that cause a resultant motion. The total or resultant thrust can be resolved into two vectors: lift, the vertical component overcoming weight, and thrust, meaning the horizontal component which overcomes drag. For simplicity, this and other diagrams do not include forces in any direction except in the picture plane. In turns and pullouts, G-loads multiply as a measure of the aircraft's acceleration. The total resultant G-load acting on a Cobra in a turn is a centrifugal force pulling the aircraft outwards. To overcome this force, the resultant thrust must be an equal and opposite centripetal force producing enough G capability to sustain the turn or pullout without loss of airspeed or altitude. In turns, the amount of G-load is directly proportional to the angle of bank. The rotor system must produce enough G's to sustain it. A 30-degree angle of bank measured from the vertical develops a G-load of 1.15 G's. The rotor system must produce 1.15 G's to sustain the bank. A 45-degree angle of bank develops 1.4 G's, still well within the G capability of an aircraft weighing 9,500 pounds, with rotor thrust available of 21,000 pounds. A 60-degree angle of bank develops 2 G's. A Cobra with 9,500-pound gross weight begins to approach the limits of the rotor system's available thrust. Once again, here's why. The total G capability of the rotor system, or the maximum amount of thrust available, is 21,000 pounds on a standard day. Divided by the gross weight, it can produce 2.21 G's maximum. So you have very little left for maneuvering. Remember, the rotor thrust available deteriorates at higher density altitudes or other variations from the standard conditions. A 72-degree angle of bank develops 3 G's, well beyond the G capability of a Cobra weighing 9,500 pounds, or just within the capability of a Cobra weighing 7,000 pounds. Yet the highly maneuverable Cobra can achieve angles of bank up to the vertical and beyond. To you, the pilot, this means an almost certain danger of loss of altitude, airspeed, or both in steep turns that set up G-loads beyond the G capability of the rotor system. The same general principle applies to high-speed dive recovery. In any low-G maneuvers, such as tactical pushover, a right rolling reaction may occur which is independent of pilot input. With SCAS operating, the roll tendency is initially corrected automatically and may not be apparent until approaching 0G. Without SCAS, however, if the rate of roll is not corrected when it begins, roll may accelerate to a point not correctable by the instinctive pilot response of left cycling. In either case, recovery may be quickly accomplished by application of aft cycling. If SCAS is on, leave it on until recovery is complete. Airspeed or external wing stores have little effect upon the roll tendency of the aircraft. Exact combination of factors which place the pilot in a situation beyond his capabilities is remote. As in fixed-wing aircraft, for any given angle of bank, the turning radius varies in direct proportion to the square of the airspeed. For example, for an angle of bank of 30 degrees, the radius of turn at 160 knots is 4 times greater than while flying at 80 knots. This can be critical in restricted areas, such as ravines at low altitudes. You should plan ahead for any given angle of bank. High-speed dives are affected by several aerodynamic flight characteristics. Rates of descent are far higher than in the Huey, with 3,000 feet per minute common in the Cobra. This is due to the slim silhouette, producing less drag, as well as the Cobra's higher airspeed capability. The higher rates of descent can make recovery from high-speed dives a critical maneuver, particularly with high gross weights affecting G capability. Wide differences can be found in pullouts. It is important to know the variables that affect rate of descent and therefore the altitude loss after pullout begins. Different airspeeds cause important differences in the Cobra's pullout capability. Here, two Cobras with other variables equal demonstrate that the faster aircraft develops a much faster rate of descent. It can be expected to lose far more altitude at pullout. If you're used to pulling out over the treetops, better check your airspeed and rate of descent before you try this in a Cobra. Different power settings are another important variable that affect rate of descent and altitude loss after pullout. These two Cobras are preparing to dive with only one variable changed, in this case, the power setting. Both Cobras are flying at an airspeed of 60 knots, altitude 5,000 feet as they initiate dives together. However, one Cobra has a 20-pound torque setting, the other 30 pounds. The Cobra with a 30-pound setting quickly builds a much greater rate of descent. By the time it reaches 2,000 feet, its rate of descent is 5,000 feet per minute. The Cobra with the lower torque setting descends more slowly, reaching 3,500 feet per minute at 2,000 feet altitude. Gross weight is an important factor affecting rates of descent during a dive and G loads during recovery. Tactics will require different dive angles. A steeper approach will build a faster rate of descent, causing greater G loads during pullout. Recovery from a dive has the same relationship to G load generation as the angle of bank in a turn. The more abrupt the pullout, the greater the loss of altitude. The answer is to reduce the severity of the recovery. The vertical fin also affects the Cobra's flight characteristics. Its cambered section generates thrusts at high speed. The vertical fin produces thrust from left to right to offset torque, thereby unloading the tail rotor, making more power available to the main rotor system. As the tail rotor is unloaded with increased airspeed, you will need to trim the aircraft with the right pedal. These, then, are the major aerodynamic flight characteristics of the AH-1 Huey Cobra helicopter, especially as they are affected by high speeds and high G loads. Remember, over 120 knots, severe maneuvers like wingovers and fast rolls will be affected by transient torque. Angle of bank is important to development of G loads and determines the severity of turns. For a given angle of bank, the turning radius varies in direct proportion to the square of the airspeed. For the most critical maneuver, the pullout, altitude loss at different gross weights, altitudes, airspeeds, rates of descent, rotor RPM, and power settings can be critical to pilots accustomed to the slower, higher drag Huey. We encourage you to make use of the improved capabilities of the Cobra to their maximum. You can do so with confidence if your attention to aerodynamic flight characteristics is precise, knowledgeable, and timely.
operations of an insurgency nature have underscored the value of the helicopter in a combat situation. The Huey Cobra, the Army's first attack helicopter, is the latest in this line of military aircraft. During the next few minutes, we will see the Huey Cobra in tactical situations typical of what might be experienced in day or night operations.
Hey, Dwight, how'd it go last night?
Oh, it wasn't too bad, but the Lurks really had a rough one.
Get him out okay?
Yeah, we got him out all right, but touch and go for a while.
Many good pointers can be learned during discussions of personal experiences.
They've been talking to us for about, I guess, 5-10 minutes or so. Yeah. Said they had movement on 3 sides.
Yeah.
And what they wanted to do was to pull back down to the south here for an extraction. So we were talking about getting it all set up. And all of a sudden, the radio went completely silent. All communication.
You get a strobe?
No, we didn't get a strobe or anything. We called and called them for about 5 minutes. And nothing. Then all of a sudden, right out of the blue, you know how the alerts are, we got this.
Charlie Lost 35. This is Silent Walker, 1-6. I have Papa Zulu, 50 meters, 170 degrees from my location. From my flare. Fire, 360 degrees, 20 meters. Over.
Charlie 35, roger. There's the flare out at 10 o'clock. He wanted us to suppress the area about 20 meters to his north while he moved down south for extraction.
Receive any silent extraction?
No, once we suppressed the area and started to pull out, we didn't have any trouble at all with it.
Leon, your team is going to be on standby for Mad Merlin 1-6 this afternoon. Presently, 1-6 is located just south of LZ Oscar. He can be reached on frequency 54.4 Fox Mike. Mad Merlin 1-6 is conducting reconnaissance operations in the area just south of LZ Oscar, and your mission for the remainder of the afternoon will be to give him any type of support that he needs. Are there any questions? Okay, let's go to the enemy situation. A guerrilla-sized unit has been sighted here last night. To the north of this guerrilla unit is a regimental-sized unit. To the east of the regiment, a rear supply unit. You can also expect light automatic weapons fire from this ridge line. The weather in the entire operational area during the afternoon will be thunderstorms and heavy winds. For fire support, contact Firebase Yogurt, frequency 44.4. For TAC Air, contact me. Any questions so far?
How about rearming and refueling?
Rearming and refueling will be conducted at Firebase Trigger.
Are you sure about that, sir? The last time I was in there, they were low on 7.62 and 40 mike, and they wouldn't let us have any rockets. Have they gotten that squared away yet?
Affirmative. Logistics are available there. Any other questions? Okay, good luck.
Cliff will be flying with Mr. Bledsoe in aircraft 720. Mr. Hopp's going to be flying with myself in aircraft 116.
Among the factors brought out during this briefing was the mission, the location of the enemy forces, the types of units and weapons engaged, the terrain and weather, and the troops and equipment available. These factors are summed up in the acronym MET. Prior to takeoff, there are certain checks the crew will conduct. These fall under the heading of armament pre-flight. It is important to always assume that the weapons are loaded and hot. Next, ensure that the area to the front of the weapon is clear. The timing of the XM-18 should also be confirmed. Be sure that all cannon plugs are connected and seated. The seating of the rocket pod contacts must be checked. Finally, check to be sure that the aircraft is free of grounding wires.
Okay, Leon, let's get it in here, man. Control.
The checks that the crew has just completed are checks that should also be conducted as a post-flight inspection. The purposes of such checks are obvious: to ensure the proper functioning of the weapons in order to make the most efficient use of this vast fire capability. Most requests for direct fire support come from the ground commander. He communicates his location and the location of the target relative to it.
Mad Maryland 16, Cobra 36, over.
Cobra 3-6, this is Mad Maryland 1-6. I have you in sight, over.
Maryland 16, this is Cobra 36, situation report, over.
This is Maryland 1-6. My unit is pinned down approximately 10 meters north of the road, running east and west to your 12 o'clock position. Enemy target, 140 degrees, 200 meters from my location, over.
This is Cobra 36, top smoke mark your location, over.
Top smoke. This is Merlin 1-6. Smoke is out. Identify, over.
The tandem seat arrangement and wraparound canopy provides excellent visibility for the gunner and the pilot.
This is Cobra 36, identify red smoke, over.
This is Mad Merlin 1-6. Red smoke correct, over.
Cobra 3-4, this is Cobra 3-6, fire mission. Enemy position 140 degrees, 200 meters from red smoke.
Friendly troops 10 meters north of road. Make 3 runs north to south, XM-18 only. Hold 25%, break right. Fire no closer than 75 meters to friendly troops, over.
Cobra 3-4, roger.
Mad Maryland 1-6, this is Cobra 3-6. Am I hitting your target, over?
Cobra 3-6, this is Merlin 1-6. Roger, over.
Why did Cobra elect to engage this target in this direction? And what were his instructions? First, the mission is a troops and contact mission. Target 140 degrees, 200 meters from red smoke, immediately orients the attention of the wingman and alerts him to the target area relative to the friendly position. From north to south indicates that the attack will take place from a northerly direction to the south. Making 3 runs allows the wingman to plan his ordnance expenditure for each run, and XM-18 only clearly states the ordnance to be utilized. Changes in ordnance selection can be made as the contact develops. Limiting factors dictate that fire is to be placed no closer than 75 meters from the friendly troops. Total ammunition expenditure will be 75% of ordnance on board. In this unit, a 25% minimum is carried at all times to cover unexpected situations.
This is Merlin 1-6. As soon as you commence your next pass, I'll maneuver my people to the west and secure the LZ for pickup, over.
This is 3-6, throwing in hot with rockets, over.
Good planning and an ordnance payload equivalent to 8 105 batteries means that the Cobra's attack capability is being realized to the fullest. There can be no substitute for correct decisions made with a minimum of delay. Note that accuracy has further been increased by the capability of the Cobra to perform high-angle dives. Essentially, briefings for night missions encompass the same points covered for day missions. However, 2 areas that require additional consideration are aircraft and target lighting, and terminal approach and logistic bases for the replenishment of ammunition and fuel. Why? As experience has taught us, an airfield could fall below minimums within the span of a flight. In such an emergency, we must plan on an alternate airfield or consider frequencies for radar contact.
let me see now. We depart northeast into quadrant number 1 and contact the Tactical Operations Center. And then we hold northeast at 1,000 feet and await further instructions. Is that correct?
Affirmative, that's correct.
Well, sir, where will Brilliant Bum stand by, and what support do we have if he can't make it?
Brilliant Bum will be on ramp alert at this location. If he can't take off, we have artillery for flare support, and we do have mortars. You have the frequency for artillery. For mortar flares, call me, okay?
Right.
Any questions, gentlemen?
Yes, sir. Say again the call sign of Firefly and the frequency we can contact him on.
Call sign is Brilliant Bum 11, UHF 221 nothing, Fox Mike 38-7.
Okay, sir. Now say again the frequency and call sign of the artillery.
Artillery is Red Leg 77, Fox Mike 43-6. Are there any more questions?
No, sir. No.
Well, then that's it.
Okay, now Dwight, this Hill 206.
This briefing has underscored an important point. Alternate logistic bases in a combat situation are not free of attack. We might find upon returning to home base that it is necessary to go elsewhere. We must always know which bases we can go to and the logistics they can provide. Instructions have been given to this fire team to report to quadrant number 1. This is an area free of artillery fire. Quadrants are obtained by dividing a specific area into 4 parts with one line running north to south and the other east to west. Quadrants are always numbered clockwise.
Anaconda 3, this is Charlie Hoss 36, airborne at this time. Request further instructions, over.
This is Anaconda 3, stand by, over.
Charlie Hoss 36, roger, out, break. Hoss 33, this is Hoss 36, go hot, orbit quadrant 1, await further instructions, over. Roger, out.
With the fire team airborne and orbiting quadrant 1, the Tactical Operations Center can evaluate any situation and effectively employ Hoss 36 in minimal time.
Charlie Hoss 36, Charlie Hoss 36, Anaconda 3, illumination en route. Contact Brilliant Bum 11, receiving small arms fire along the southern perimeter. Request you attempt target identification and engage, over.
Roger, out. Break. Hoss 33, this is Hoss 36, as you monitor, over.
That's affirmative.
Bum 11, this is Hoss 36, say your location, over.
This is Bum 11, airborne this time, estimating your location in 03. I'll have 1 plus 30 on station, over.
This is Hoss 36, roger. To the south, you can see extensive tracer fire. I'm orbiting over that location at 1,800 feet. Report 1 minute north of the camp, and I'll cover you going in, over.
Roger. The foregoing conversation indicates close coordination between all elements. The crew's full understanding of the problems of a night attack is critical to the success of any mission.
Hoss 36, this is Bum 11. 1 minute north. I have the tracer fire in sight, over.
This is Hoss 36, roger. I have you in sight. I'll come up on your right side. Mark the area of the tracer fire about 100 meters south of the perimeter. On your mark, I'll commence fire, making runs from east to west with a right brake, over.
Brilliant Bum 11, Wilco. I'll be marking from 500 feet, over.
Bill, let me know when we reach 1,000 feet. Call out every 100 feet after that. I don't want to go below 500 feet.
Roger.
night mission has brought up several points well worth remembering. They are the difficulty of orienting on a target at night, the blinding effect of weapons, the glare from cockpit lights, and the fact that target fixation can be avoided by close coordination between the pilot and co-pilot, and fixing a definite disengagement and recovery altitude. Finally, it was shown that Firefly is not only a highly selective illumination method, but the time on station is the only limit to its employment. The flare, while being the most readily available means of target illumination, has basic drawbacks, such as its short duration and high intensity. We have just seen the Huey Cobra in tactical situations typical of what might be experienced in day and night operations. Now let us review what we have learned. Among the factors brought out in any briefing are those to be found in the acronym MET. While tactics are subject to change, tactical considerations remain the same. Prior to takeoff, there are certain checks the crew will conduct. These checks fall under the general heading of armament pre-flight. Once in flight, the tandem seat arrangement of the Cobra's wraparound canopy provides excellent visibility. The stability augmentation system ensures the Cobra's accuracy as a firing platform. Another characteristic of the machine is its ability to perform high-speed maneuvers. High-angle dives increase the Cobra's accuracy, while the high maneuverability and a slim silhouette reduce its susceptibility to ground fire. Essentially, briefings for night missions encompass the same points covered for day missions, with two additional areas that require special consideration. These are aircraft and target lighting, and terminal approach and alternate logistic bases. Instructions have been given to this fire team to report to a quadrant number. Quadrants are obtained by dividing a specific area into 4 parts. Finally, it was shown that Firefly was a highly selective illumination method, and that time on station is the only limit to its employment. These and other points indicate that while tactics change from mission to mission, certain tactical considerations will remain the same. Once they are understood, the Huey Cobra assumes its rightful role as a major offensive weapons system.